And hello, welcome back. So in the last video we talked about Reynolds average, Navier-Stokes time averaging procedure, and then we got these three so-called Reynolds stress-like terms. But it's just, I think you can model this as a turbulent heat flux of some sort. So this is our closure problem. Of course, there's the LES version of it. There's the LES version of closure. Okay, so instead of time averaging, we do filtering. So this is slightly different. We still have our terms here, but instead we do filtering. Okay, so we do filtering for LES instead of time averaging. Okay, this is slightly different because this is usually a spatial kind of thing. Okay, and instead of this, we will have a filter function. So the most generic form of the filter function is we have a dt prime here, which we will just integrate from minus infinity to infinity. And then of course we'll do integration over space as well. Minus infinity to infinity. Okay, that looked very weird. Integration minus infinity to infinity. Alright, that's better. So this will be with respect to some space coordinate, we'll call it dr now. So okay, so hopefully you're already familiar with filter. Hopefully you're already familiar with filter. Here's a x minus r and t minus t prime kind of a version, but just know that this actually is an integral or double integral, whatever you have it. Okay, the del by del x, you can of course bring it out because it's got nothing to do with either t prime or r. R is a distance from wherever you are having x at. So there's a spatial filter, and there's a time aspect as well. So this is the most generic form of filtering. Okay, so again we will need to expand this out. Okay, we'll need to expand this out. Don't mind the Microsoft Word bug. Alright, we'll expand this out and we'll do exactly the same thing. Expand out. So we'll just substitute ut equals to this inside. So I'll just copy and paste here. So indeed, this will be the filtered parts and this will be the unfiltered part. Okay. So we will need to do a few more terms out. Okay. We'll need to filter the first term. So we have a double bar over it. Second term, double bar over it. Third term. Okay. Oh shucks, why did I do that? Okay. That's very weird. That's better. Yeah. And this term should have a t prime at the back. Right. Alright, so these of course, yeah, I should bring this whole thing out now. Okay, this of course we'll need to decompose further. Then we'll have of course our Leonard stress and whatever decomposition looking like terms. So we can do it like so. So 1, 2, 3, and 4. And I'll get this out. And so we have this sort of equation here after filtering. Now, I think similar to this term, this what do you call that? yeah, this term here, we can also, if you remember your Leonard's decomposition, we eventually want to get this filter a little bit out of the way. So what we do is we do this, okay, we plus this term, then we kind of subtract it away as well. Alright, these ones we can group together. Alright, and then the rest of the terms kind of follow over here. Now if you remember our large eddy simulation, this one is kind of analogous to the Leonard's stress tensor. Okay, and this one I can cancel out. It's not supposed to be there. Okay, this one is kind of like the Leonard's tensor. This one is kind of like the cross tensor. This one is kind of like the Reynolds tensor. Now together, all these three actually form some sort of subgrid tensor. So what we usually like to so-called model this as, or rather, when you kind of do you kind of do this over the x, y, and z directions. So instead of, okay, you in x, y, and z, we can just replace u with v or w, x with y or z. So I can just write the following. Okay, so ui, I'll use ui here to represent, okay, I'm doing x, y, or z direction. Likewise, x I'll replace with xi. Okay, so this isn't actually the Leonard's tensor yet. You have to do it, or the subgrid tensor yet. Subgrid tensor-ish thing, like an analogous to the subgrid tensor kind of thing. It's not that yet because you have to do it over the x, y, and z directions. So then once you do that, then yes, you can consider the terms I was pointing to, the subgrid tensor. Okay, hopefully I put the I on everything. So I put the I here, 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 and all the relevant terms. So this is sort of analogous to those Leonard stress terms. This one is kind of like the cross terms. This one's kind of like the subgrid, the Reynolds terms. Okay, what we kind of do for closure is that we model this as, alright, we model this as this, like so. Okay, some sort of subgrids heat flux. Okay, so this is sort of like a subgrid heat flux kind of thing. So this is what we need. This is the closure problem we need to do. And substituting this back, we can take a look at our original equation. Okay, we can take a look at our original equation, which is, I believe, over here. Okay. Okay, I think I forgot the bars here. Okay. Anyway, yes, this one there should be bars here. Sorry, let me quickly correct that. Yeah, so all these things here should be having a bar on them. There's a typo. Yeah, so we go back to our original equation here. These filter equations here. Okay, and yeah, we sort of get it in this form. Okay, So we have this left hand side, and it should be equal to this Laplacian term here. Okay, so I'll get the Laplacian term down. Get the Laplacian term down, and then I'll get this term down as well. Plus, of course, we'll need a time derivative term because that doesn't disappear. So the time derivative term. Okay, there's a time derivative term here. So this actually represents this term here. So I'm just going to copy and paste this term here. All right, and I'm going to put this over to the other side. All right, and yes, so we can see a slide. And this is the LES version. Okay, and then I'll just for your reference put the Rand's version over here. Okay. Of course, in the unsteady state, unsteady Reynolds average Navier-Stokes, the Rand's version, you'll be like that. Okay, so that's the closure problem we need to do. Okay, and of course this you can sort of model it as the subgrid stress, so-called subgrid conduction kind of thing. It's turbulent conduction. All right, so now we have we see what our closure problem looks like. This is for the LES, and this is for this one's supposed to be for the Rand's version. I think again I made another typo. This should be the Laplacian term. So let me get the Laplacian term down. Yeah, this should be the Laplacian term over here. Okay, so let's get the Laplacian term. There's a error there. Okay, so where does it go? Again, here needs a bar, a few bars. Yes, okay, but this actually should equal to Laplacian anyhow. So I'll just paste the Laplacian term there. I made a mistake last time. Okay, so the Laplacian term should be there, over here. Okay, that's where the Laplacian term is, and it should be over here. Yes, that's the Laplacian term. All right, so this looks more right now. Okay, so this one is should also come here. All right, that should also come here, the Laplacian term, and then now we start having to do some closure. So this is the closure for the LES version. This is the closure problem we have to solve for the Rand's and the Rand's version. Now this should be the final form. Okay, hopefully there's nothing more. Okay, I can also change this here. All right, I'll expand this differential out. Okay, and now obviously this term is 0. This term here, the filtered filtered velocity, the continuity equation, that equals 0. So I will just copy this, cut this, and paste here. So this is the final way it should look, and this term is actually just this term over here. All right. Yeah, so this term here is actually this term here, so there's no difference there. Hopefully you know what's Einstein notation. I just contracted it for convenience. Okay, Anyway, yeah, so now we have to do some closure, and I want to introduce you to how we do the closure. Okay, so closure is mainly done like so. Okay, whether it's for LES or UREN's model, whether it's for LES or UREN's model, the way you close, okay, is this. So you have this term here. It will be, or rather you have this term here equals to minus alpha. Okay, it should be some sort of conduction. Okay, partial t partial xi. All right, I think again I made a error. I think to correct it. This should be divided by rho Cp. All right, that's better. I think that should settle the units. But okay, this is more or less the same thing. Where I'm trying to say, yeah, this thing is actually modeled by some kind of subgrid conduction term. So I just changed all of this. Alright, so that should about do it. Yeah, so this is all modeled through some subgrid conduction term here. Now this term is modeled as such. So what we do is just copy and paste. What we do is just copy and paste, and this is what we get. Alright, and this will cancel with this to give a plus. K over rho Cp is some alpha, right? So this is a turbulent conduction term, sort of thing. All right. So this is a turbulent conduction term, similar to how we model the velocity part of the turbulence, the momentum turbulence has some increase in kinematic viscosity. We do the same for turbulent flow of temperature and conduction. So this actually becomes alpha t. Okay, this actually becomes alpha t. All right, and if this were constant with, let's say, position. If let's say this were constant with position, we can just bring this out, and what we'll get is something like that. And this is just the Laplacian of t. So nabla squared t bar. Okay, oh, this should be in terms of t bar, yes. Alright, so what you will see normally is an expression like this. Okay, you have alpha and alpha t. Sometimes this is you see an epsilon there. It's like the eddy heat diffusivity or something like that. But this together we call it alpha effective, right? It's alpha effective. Okay, some in CFD code you'll see some alpha effective being mentioned, and this is what it is about. All right, and this is basically the final form. Now, if you do the same for this this part, we get we get the same result. When you model these three, you model these three things as simply you model it simply as this, okay, and it's the same idea. You will still get the same equation over here. All right, when you replace this with these three terms, then you would get these terms here as well. So regardless whether we use RANS or LES or URANS, unsteady Reynolds average Navier-Stokes, the final equation form looks like this. It just depends what alpha t is, right? Okay, the equation form looks the same, but alpha t is somewhat different for both between RANS and LES. Okay, RANS, URANS, and LES. So it is a slightly different value, namely because, again, here you, in RANS and URANS, you model all the turbulence. This one you kind of model 20% of the turbulence and you try to resolve 80% of it, ideally speaking. So it makes sense that your alpha t may switch a little bit between both of them, just like how your turbulent viscosity kind of switches between both of them. So yeah, next time we'll probably want to talk about the closure model and the turbulent Prandtl number. What does that have to do with alpha t? And it's very closely related to alpha t. But next time then I'll talk about it. So thanks for watching. Pardon the errors that I've made, a lot of errors, typo errors and all. But hopefully that helps you get a little bit more of an idea where all these terms are coming from. Yeah, where all these terms are coming from, and yeah, that hopefully clears some of the potential confusion, especially when you try to add another transport equation into this whole thing. So yeah, this is what the final equation looks like. All right. So I'll see you in the next video. Thanks for watching. Bye bye.